Hi, I'm Brian Mallow, and I'm speaking with Yoseob Yoon, who's one of the 12 finalists in this 4th annual Research SLAM at Berkeley Lab. Yoseob, hello.
Hello. Thank you for the invitation.
Oh, yeah. So congratulations on being one of the finalists. Have you done this Research SLAM before or anything like it?
No, this is my first time.
How are you feeling about it?
A little bit nervous because I have to speak in front of many people. At the same time, I'm very excited to share my research, and in a way that it's going to be exciting for everyone, not for just my colleagues.
Not your colleagues, yes. Bring it to the people. So I think it's fascinating. I don't think people realize that, a scientific research career is a full-time job. And then to also do outreach on top of it can be a lot of work. So this is a really fun and interesting form of public outreach. Do you do any other public outreach? And do you think it's important or fun or?
I have done some, I was in Boston before I came to Berkeley, and there in the Museum of Science, Boston, I did some outreach, I did some demonstrations in front of public, and yeah, I was showing some experiments to kids, and it was fun.
Yeah. So this is sort of an extension, but it doesn't have to be down to the level of children, at least. At least it could be, lay people that are adults. Mm-hmm. So yeah, let me ask you about your son. You're a physicist, right?
Yeah, that's right. Mm-hmm.
And a postdoc, if I didn't say. And where are you from?
I was born and raised in South Korea.
And did you begin your academic studies there as well, at least as an undergrad?
So I was actually in Berkeley for 1 year as an undergrad, as an exchange student, and then I went to Boston for my graduate studies, and then came back to Berkeley as a postdoc.
Excellent. Oh wow! So, and how young were you when you figured out you wanted to be a scientist? Did you always know? Was there ever any other career path that you contemplated?
So as soon as I started learning about atoms and molecules and how they move around and how they vibrate and they react, they change their shape and so on, it was so fun to imagine those things in my mind. So since then I decided to become a scientist, and I wanted to learn how they work, how they form new molecules and so on. If I were not a scientist, I probably would be a classical music pianist, because I just play piano for fun. Yep. Interesting.
And I guess, do you see connections between those two things? I know that music is mathematical.
Mm-hmm, mm-hmm. But of course, I don't think of math when I'm playing music, but yeah, I just enjoy and I like those harmonies between notes, and yeah, when I'm playing music.
Is the joy you get from music, is it different from the joy you get from doing your science, or is there anything, do they have anything in common, or are they completely different? Do they satisfy different things for you?
I would say they're similar and different. So for example, if I want to play one single piece of classical music, then I need to practice a lot. And if I complete complete one piece, then it feels so satisfying. You of course have to take care of a lot of different things, like volume as a function. Yeah, volume and a lot of touches. Yeah, and in science, I would say it's a little bit similar. As an experimentalist, you do experiments, and you have to take care of a lot of different things. And once you take all the data that you want, then it's so satisfying. And yeah.
Yeah, interesting. So you started at university. Were you already, you were interested in atoms and stuff? So it pretty much means physics was the path. And then you he even came to Berkeley early. That's really fascinating. And now you're a postdoc there, and you're in energy sciences and material sciences. So what are you doing? What is your postdoc work there at Berkeley?
So I am using laser beams to interrogate some material properties. So I shine laser light to some certain materials, and then I look at the reflected or transmitted light and analyze the light. Then I am able to tell what's going on inside the material. So I am always trying to think of how light interacts with matter. And in certain cases, light interacts with matter so strongly so that they mix together. So they become like a hybrid light matter quasi particles, and they behave weirdly. So I am trying to learn like how they work, how they interact, and how I can make it useful in real world applications.
And when you say real world applications, do you mean real world applications, or do you mean science fictional world applications? Because the name of your presentation for the Research SLAM is Lightsabers at the nanoscale. Are you trying to make applications for the real world or for some science fiction fantasy Star Wars world?
Yeah, so of course my talk is about lightsabers and how to make them. So people can make those in a lab, and so basically there are a few properties of lightsabers. One of them, the most important thing is that they have to repel each other. So normally light beams doesn't do this. So to make light repel each other, that's where the hybrid quasi-particles come into. I make hybrid particles mixed with light so that light interacts with each other. And I use that lightsaber not to battle our enemies, but to make an optical switches that can be used in computer chips. So normally in computers, like there are CPUs, GPUs, those are made of chips that work with electrons. A lot of electrons, you need to flow them, and they sometimes generate heat, and those are main limiting factors for modern computer chips. And if you use optical light, then it can be much faster, much more efficient. So that's how I'm envisioning my research to be applied in real world. It's not applied yet, but I'm hoping to make some in the future.
Are you saying visible light replacing electrons, like
That's
circuitry
right.
that somehow utilizes? Interesting. So that's a radically different design for a computer.
Yeah, that is very different in the sense that electrons, they normally interact very strongly, but the problem is they are inefficient. So they interact with other particles a lot. So when they flow through the wires, they generate heat, and that's the main problem. For example, if you use a laptop for a while, then it gets hot. On the other hand, if you use light switches, then it doesn't. When light passes through an optical fiber, for example, it doesn't generate heat a lot. So yeah, that's the main advantage.
Interesting. So let me ask you, you're one of the 12 finalists for the Research SLAM, and we're coming up on it. How are you feeling about it?
Yeah, I'm feeling very excited, especially to share my analogy about lightsabers of the optical switches. I feel it's exciting. I think it's fun. Of course, I think a lot of people have imagined how to make a lightsaber. So I think there's a good connection between a real research and general public.
Yeah. Do you have you get to use one slide, or really it's a virtual background in this case, and you have 3 minutes and it has to be accessible to the general public. And you also get to choose an intro song, a walk-up song to come on stage to. Have you decided what to use?
Yeah, it would be the Star Wars main theme.
Perfect. For lightsabers at the nanoscale. And so very interesting. So thank you very much for taking the time to talk to me, and good luck in the Research Slam.
Thank you very much.